Welcome dear learners. We are continuing Unit 3 Introduction to Nanomaterials. In the present module, we are discussing on fullerenes and carbon dots. The contents of this module are fullerene, discovery, synthesis of fullerene, physical properties of fullerene, chemical reactions of C60 or fullerene, carbon dots, synthesis of carbon dots and applications of carbon dots. First of all, we are discussing about fullerenes. You know the fact that fullerenes are allotrope of carbon. Fullerene belongs to carbon-based nanomaterial. This fullerene molecule is very familiar to you, and in this module we are discussing the fullerenes, its features, its preparation, properties, discovery, etc. in the first part. Fullerenes are third allotrope of carbon after graphite and diamond. Fullerenes were discovered in the year 1985. Fullerene consists of carbon atoms connected by single and double bonds so as to form a closed or partially closed mesh with fused rings. Here it is very well clear that there are so many rings, and these rings are fused together to get a spherical type arrangement or a hollow type arrangement or a mesh type arrangement. Moving on to the discovery of fullerene, the first fullerene was discovered in the year 1955. I just mentioned this point, and the discovery was performed by three renowned scientists. They are Harold W. Kroto, Richard E. Smalley, and Robert F. Curl. A group of these three scientists discovered fullerene in the year 1985. Now, these scientists, during their discovery, got a cage-like molecule composed of 60 carbon atoms. That is, they got C60. And C60 is obtained during the vaporization of graphite rods by using laser in an atmosphere of helium. This was actually their synthesis procedure. They vaporize graphite rod with the aid of laser, and that experiment is performed in an inert atmosphere of helium. Under these conditions, the team of three scientists got C60, which is the first discovered fullerene molecule. Now, the scientists won Nobel Prize, which is in the year 1996. They won Nobel Prize in Chemistry. That is, the Nobel Prize in Chemistry in the year 1996 was awarded to the discoverers of fullerene. That is, Robert F. Curl, Harold Kroto, and Richard Smalley for the discovery of fullerene. Now, the name fullerene. There is a history behind the name fullerene. The C60 was named as Buckminster fullerene, or simply the buckyball, and this name is after an American architect. Note the fact that the name is after an American architect, not a scientist or a chemist. Then what is the reason? Why the name Buckminster fullerene? R. Buckminster Fuller was a structural engineer. He developed a geodesic dome, and that geodesic dome is constructed on the same structural principles as that of the C60 molecule. The Buckminster Fuller is here, and his geodesic dome is shown on the right hand side. So, you have to keep in mind the fact that This geodesic dome developed by the architect R. Buckminster Fuller is in the same structural principles as that in the case of Fuller. So, the C60 molecule has some structural arrangement which is analogous to this geodesic dome. That's why C60 is named as fullerene under this geodesic dome nomenclature, under this geodesic dome name. Buckminster fullerene or C60 is shown here. We are now discussing some details of Buckminster fullerene. Buckminster fullerene or C60 is the fullerene molecule containing pentagonal and hexagonal rings in which no two pentagons shared an edge. It is a very important feature of the structure of the C60 molecule. In the C60 molecule, you can see the presence of pentagons as well as hexagons. However, no two pentagons or no two hexagons will share an edge, but a pentagon share its edge with a hexagon and vice versa. But there is no sharing of edge between two pentagons or two hexagons. That's the important structural characteristic feature of the Buckminster fullerene C60. It is also most common. This C60 is most common in terms of natural occurrence, as it can often found in the carbon soot, in the carbon flame. So, this is the more stable fullerene. This is the most common fullerene. So, the most common and stable fullerene is Buckminster fullerene, that is nothing but C60. The structure of Buckminster fullerene is highly interesting. Here you can see 60 carbon atoms joined together by single as well as double bonds to form a hollow sphere, and in that hollow sphere you can see the presence of 12 pentagonal rings and 20 hexagonal rings or faces. That means C60 comprised of 20 pentagons and 20 hexagons and 12 pentagons. The pentagon is shown here. It is a cyclic form, consists of 5 carbon, and the hexagon consists of 6 carbon. In Buckminster fullerene, there are 12 such pentagons and 20 such hexagons. This is the illustration of the Buckminster fullerene. In that rotating structure, you can see pentagons and hexagons, and you have to remember it again, the fact that no two pentagons share an edge and no two hexagons share an edge. This is a design that resembles a football or a soccer ball. That is the peculiarity associated with the structure of Buckminster fullerene. Now there are several other fullerenes known. We are moving into the details of other fullerenes. Other fairly common fullerenes is C70. The most common one is C60 that we know well. In addition to C60, we can see there are some other fullerenes, and a common fullerene is C70. But fullerenes with carbon atoms 72, 76, 84 and even up to 100 are commonly obtained. But their stability is very poor when compared with the C60. So, there are other fullerenes also. Fullerenes with fewer than 60 carbon atoms have been called lower fullerenes, or lower fullerenes are associated with the carbon atom less than 60. In a similar way, there are fullerenes with greater than 60 carbon atoms. The fullerenes that contain 60 carbon atoms, above 60 carbon atoms, are called higher fullerenes, or higher fullerenes having more than 60 carbon atoms. Now, what are lower fullerenes? The C20, that is a group of 20 carbon atoms, forms a fullerene, and C20 is the smallest member of the fullerene family. It is a lower fullerene. This is because C20 consists of only 20 carbon atoms, which is far less than the baseline, that is 60. So C20 is a lower Fullerene. This C20 is having dodecahedral cage structure. Its structure is also a cage, and that cage is known as dodecahedron, or this C20 is associated with a dodecahedral cage structure. The most stable structure is theoretically established, and that consists of pentagons only. This is another characteristic feature of the lower Fullerene C20. C20 is having a dodecahedral cage structure which comprised of pentagonal faces only. You know the fact that in the case of C60, there are 12 pentagons or pentagonal faces and 20 hexagonal faces. But hexagonal faces are absent in C20. There are only pentagonal faces. This is the structural representation. Here you can see pentagonal faces only, and there will be no hexagonal faces. So, whenever we are discussing about C20, we can say two important points. It is a lower Fullerene, and it consists of only pentagonal faces. Now we are looking on to higher Fullerenes. Some common higher Fullerenes are here. It is C70, that comprised of 70 carbon atoms. C72, there are a total of 72 carbon. C76 and C84 belongs to the category of higher Fullerenes. So, these four shown in the screen are examples for higher Fullerenes. They consist of carbon atom greater than 60. So, the good examples for higher Fullerenes include C70, C72, C76 and C84. Many other higher Fullerenes are also reported, but we specified it because owing to their existence as well as stability. And it should be noted that the Fullerenes up to 100 carbon atoms are reported. Some very high carbon Fullerenes are also known to exist, but their stability is very poor when compared with the stability of our Buckminster Fullerene, that is C60. Now we are looking on to the synthesis of Fullerene. Fullerene being a carbon based nanomaterial, we know there are several methods for the preparation of the nanomaterials. So, Fullerene being a carbon based nanomaterial, and that Fullerene can also be prepared by several methods. We are looking on to some popular methods for the synthesis of the Fullerenes. Several methods are available for the Fullerene production, and these are some common methods. And the common methods include arc discharge method, laser ablation method, formation of Fullerene by pyrolysis of hydrocarbons. So, arc discharge method, laser ablation method, pyrolysis of hydrocarbons are three popular methods for the synthesis of different type of Fullerenes. Moving on to the first method, that is nothing but arc discharge method. In the arc discharge method of the synthesis of the Fullerene, a pulsed arc discharge method operated at a high temperature is used for Fullerene production. This is the graphical representation of the arc discharge method. Here you can see the presence of the graphite electrodes. A high potential difference is applied between the graphite electrodes. As a result of that high potential difference, some vaporization followed by condensation happens, and this arc discharge method is a very popular method for the synthesis of Fullerene. This second technique, that is laser ablation method, is a very powerful and useful technique for production of Fullerene clusters. Fullerenes with different structures, different kind of Fullerenes can be prepared by the second procedure, that is nothing but the laser ablation method. And this laser ablation method involves laser ablation of graphite in helium atmosphere. This is the procedure behind laser ablation method. Graphite rod subjected to laser ablation, that must be performed in an inert atmosphere of helium. Pyrolysis of hydrocarbons is the third synthetic procedure we are adopting for the preparation of fullerene. And in the pyrolysis technique, we are performing pyrolysis of aromatic hydrocarbons. And the pyrolysis of aromatic hydrocarbons enable the formation of fullerenes. The pyrolysis of naphthalene, which is an aromatic hydrocarbon, which performed at 1000 degrees Celsius in an inert atmosphere of argon steam, produces fullerene. This is a very significant method for the preparation of fullerene. This is the reaction that depicts the conversion of aromatic hydrocarbon, that is naphthalene, to fullerene. So, fullerene is subjected to high temperature in the range of 1000 degrees Celsius, which is performed in an inert atmosphere of argon gas, enable the generation of fullerene. Laser pyrolysis of benzene and acetylene also produce fullerene. The pyrolysis can be performed by using with the aid of laser also. Laser pyrolysis of benzene and acetylene yield fullerene. So, pyrolysis of hydrocarbon is the third common method for the generation of fullerenes. Now, we are discussing the physical properties of fullerenes. Fullerene, being the carbon-based nanomaterial, exhibits several physico-chemical properties, and now we are looking on to the specialized physical properties of fullerene. Fullerenes has several physical properties, including being soft, slippery, and having a low melting point. Fullerene is volatile in nature. That means the fullerene liquid can easily undergo evaporation or vaporization. This is the fullerene, which is a liquid, that is C60 dispersed in toluene solvent, is shown here. It is having a deep purple color, and this is a highly volatile liquid. Fullerene is not soluble in water. Moving on to the solubility, it is clear that fullerene prefers organic solvents. Fullerene is soluble in organic solvent toluene. That is why this C60 is dissolved in toluene and shown here. Fullerene is not soluble in water. That about the solubility. We are now looking on to chemical reactions of C60. There are so many fullerenes, but the most thoroughly studied species is C60. So, we are discussing the chemical reactions of fullerene by taking C60 as an example. The main chemical transformations that are possible with C60 or Buckminster fullerene could be classified into 5 important groups. That means the chemical reactions or chemical transformations of C60 can be grouped into or classified into 5 groups. These groups are discussed here. The first category is addition reaction. Formation of exohedral compounds by addition of nucleophiles or radicals, cycloadditions, complexations with the transition metal, etc. provide good examples for addition reactions. So, there are 5 categories of reactions shown by C60. The first category is the addition reaction. Addition reaction generates the exohedral compounds. The second category of chemical reaction shown by C60 is electron transfer reaction. Electron may undergo transition from one species to other. So, we are now focusing on electron transfer reactions given by C60 molecule. Chemical reduction of fullerenes can easily be achieved by reaction with electropositive alkali as well as alkaline earth metals. You know that the alkali metals lithium, sodium, potassium, rubidium, cesium, francium, alkaline earth metal, beryllium, magnesium, calcium, strontium, barium, radium, etc. are highly electropositive metals. They can donate their electrons to the Fullerene system, and such kind of reaction can be considered as electron transfer reactions. So, electron transfer reactions is another category of reaction that is shown by the C60 molecule. Now, the third category of chemical reaction shown by the C60 molecule is the formation of heterofullerene. We are familiar with the word hetero. Hetero means different. So, heterofullerene means the fullerene with some other atoms other than carbon. Fullerene consists of only carbon atoms. If you can introduce some other atoms other than carbon, then you can say you will get a heterofullerene. Substitution of a carbon atom of the fullerene skeleton for a heteroatom, for example nitrogen or boron, enable the formation of heterofullerene. That is, this is the strategy. In order to get a heterofullerene, you have to replace one or two carbon atoms of the C60 molecule with other elements like nitrogen, boron, etc. Now, the fourth category is ring opening reaction. You know, C60 molecule is a ring structure or is having a ring structure. If there are some reactions, during that reactions, if the ring is opening, ring opens up, such kind of reactions are called ring opening reactions. Producing a hole in the C60 skeleton while breaking a discrete number of bonds. C60 is a hollow structure. If you are breaking some bonds on the surface of the C60 molecule, then that ring structure will open up. The reaction enabling the ring opening is said to be the ring opening reactions. That is the fourth category of the chemical reaction shown by the C60 molecule. Now, the last category of the chemical reaction shown by C60 molecule is formation of endohedrals. We just heard about exohedrals. In a similar way, we are now focusing on the generation of endohedrals. That is the fifth category of the chemical reaction shown by the C60 molecule. Introducing and trapping of atoms inside the spherical carbon cage. You know, C60 is a molecule which is having a cavity or a cage in its center portion. It is possible to embed or incorporate some other elements in this cavity, and the result of that is the formation of endohedral fullerene. So, we have discussed 5 important categories of chemical reactions shown by the representative fullerene, that is C60. The chemical reactions we have discussed now can be pictorially represented like this. Addition reaction leads to the presence of some groups on the outer surface. That means exohedrals are produced. Endohedrals can be seen here. Some atoms are trapped in the cavity, that is the generation of the endohedrals. Ring opening reaction, here you can see some bonds are broken and the rings is opened. And heterofullerenes are formed by the replacement of some carbon atoms of the fullerene by heteroatoms like nitrogen, boron, etc. This is a heterofullerene. And electron transfer reactions is also shown here. If the fullerene gained some electrons donated by the electropositive metals like alkali or alkaline earth metal, that fullerene can gather some negative charge. So, I just put N minus here. So, this is a kind of electron transfer reaction. Thus, on a consolidation, there are 5 categories that include addition, formation of endohedrals, ring opening reaction, heterofullerene formation, electron transfer reaction, etc. All such category, the 5 categories are consolidated here, and this about the chemical reactions of on other kind of carbon based nanomaterial, that is nothing but carbon dots. What are carbon dots? The carbon dots can be abbreviated as C dots. You are familiar with the quantum dots. In a similar way, quantum dots are semiconductor nanomaterials. In a similar way, we are discussing a category of carbon based nanomaterial which is having similar structural features and properties as that of a quantum dot, that is nothing but carbon dots. Carbon dots are a new class of carbon based nanomaterial, and they are said to be the clusters, the group of carbon atom with the diameter 2 to 8 nanometer. This diameter range is very important. Carbon dots are associated with a very low diameter, and that diameter is in the range of 2 to 8 nanometer. So you can say that carbon dots are carbon clusters with the diameter in the range of 2 to 8 nanometer. They are simply carbon nanoparticles. Carbon dots can also be considered as carbon nanoparticles. You are familiar with the metal nanoparticles of gold, silver, etc. Similarly, it is possible to generate nanoparticles from carbon. That carbon nanoparticles are termed as the quantum dots, or simply carbon dots are carbon nanoparticles with the size range 2 to 8 nanometer in diameter. These carbon dots can be generally defined as a quasi-zero-dimensional carbon-based nanomaterial with a size below 20 nanometer. Even though the general range is 2 to 8, we can inculcate the carbon nanoparticles up to 20 nanometer in the category of carbon dots, because the particles up to 20 nanometer will show same properties as that of carbon dots in the range of 2 to 8 nanometer. So, on a broad definition, the size range may be up to 20 nanometer. Fluorescence is the intrinsic property or innate characteristic feature of a carbon dot. That means carbon dots are associated with the inherent fluorescence, or we can say carbon dots are fluorescent in nature. They will absorb a particular wavelength and emit a corresponding other wavelength. So, these carbon dots are fluorescent materials. This is the chemical structure of the carbon dot, and this is the illustration of the carbon dot. These carbon dots are associated with the fluorescence. Carbon dots are carbon nanoparticles. These are important features of the carbon based nanomaterial carbon dot. Now we are discussing the discovery of carbon dots. Carbon dots or C dots were first discovered by CEC and co-workers in 2004, accidentally during the purification of single-walled carbon nanotubes. So, that about the discovery of the carbon dot. In the year 2006, Yappingson and co-workers, some other team, other than those who reported in 2004, first synthesized stable photoluminescent or fluorescent carbon nanoparticle of different sizes, and they named them as carbon quantum dots. So, the actual synthesis and the naming happens in the year 2006 by a group of Yappingson and his co-workers. So, it is first reported in the year 2004, but that discovery was accidental. The actual synthesis of carbon dot happened in the year 2006 by Yappingson and his co-workers, and they named their product as carbon quantum dots. That about the discovery. Moving on to synthesis of carbon dots. We are now discussing what are various methods for the synthesis of carbon dots. This is a pictorial representation depicting various procedures for the generation of carbon dots. Carbon dot being a carbon-based nanomaterial and can be prepared by top-down methods as well as bottom-up methods. In this diagram, the first part represents top-down methods and the second part in yellow line, yellow color represents the bottom-up methods. The popular top-down methods for the synthesis of carbon quantum dots or CQDs involve arc discharge method, laser ablation method, chemical ablation method, electrochemical carbonization method and ultrasonic synthesis. At the same time, the bottom-up methods for the synthesis of CQDs include popular methods such as hydrothermal method, microwave assisted pyrolysis, thermal decomposition and various template routes. So, it is very well clear that you can develop carbon dots by adopting some top-down methods as well as some bottom-up methods. Now we are focusing on optical properties of carbon dots. I just mentioned the fact that carbon dots are associated with the inherent luminescent properties or fluorescent properties. We are now sticking on to the optical properties. The optical properties of CQDs involve several characteristic phenomena such as photoluminescence, chemical luminescence, electrochemical luminescence, upconversion luminescence. These are different categories of luminescence. Then photo-induced electron transfer and absorbance. So, the carbon dots are fluorescent or luminescent in nature. They may have various kind of luminescence and the entire optical properties are consolidated here, and that involves these 6 type of fluorescent or luminescent features. That about optical properties of carbon dots. We are now focusing on applications of carbon dots. Carbon dot are a new class of fluorescent carbon-based nanomaterials. C dot possess several attractive properties such as high stability, good conductivity, low toxicity, environmental friendliness or eco-friendly nature, simple synthetic procedures or simple synthetic routes to prepare them, comparable optical properties to that of quantum dots. These are very important characteristic features of quantum dots, of carbon dots that enable them in several applications. And the applications of carbon dots are based on their characteristic features that we discussed just now. Owing to their specialized characteristic features, properties, specialized properties, carbon dots have so many applications. This picture depicts the consolidation of various applications of carbon dots. The applications involve biological sensor development, photothermal therapy, application in photocatalysis, application in the development of light emitting diodes, chiral detection, antibacterial agent development, nanomedicine, photodynamic therapy and application of carbon dots in bioimaging. So, these are various areas where carbon dots have prominent application. That all about the present discussion on Fullerene and carbon dots. Have a nice learning experience. Thank you.